Next up, we have Dawson, who was mentored by Dr. IODs.
Right. It was a pleasure to work with Dawson this summer. If I had to describe Dawson, I'd say Dawson's a very humble person, but also ambitious. I really enjoyed chatting about Dawson's SAT scores and his disappointment with his scores, even though they were through the roof. Um, Also enjoyed chatting about the watch parties that he held when he got his AP scores back. And I'd like to say that Dawson is not really ahead of his time. He's right on time. It was just a pleasure to work with him throughout the whole summer. I describe Dawson as being very family oriented, cares deeply about his community, and is passionate about significance over success. And so I will let Dawson take it away to describe his project for this summer.
Thank you so much, Io. Let me share my screen. Hi, everyone. My name is Dawson Phan, and this summer I had the wonderful opportunity to be mentored by Dr. IODs. My project is focused on looking at modern landscapes and how we can improve them with trees. For context, I took this photo that you see in the background with my digital camera at my local public library that I often go to for work, such as for this internship. And I think it's a good example of how we can incorporate trees with our urban landscapes in a healthy way. So before we begin, I'd like to just introduce and give some background info. So human activity and development creates urban heat island effect. So the urban heat island effect is a phenomenon where urban areas such as cities face much higher temperatures compared to nearby rural areas like countrysides. As you can see on the image on the top right, the downtown area faces significantly more higher temperatures compared to the rural or suburban areas. And the causes for the UHI is that impervious surfaces and a lack of vegetation causes this. So an impervious surface is an artificial structure like a road, sidewalk, parking lot, and they're made of concrete or asphalt. So the UHI effect is bad because it can lead to many negative health and environmental effects, such as heat stroke, dehydration, exhaustion, especially for the children and elderly. It also leads to poor water and air quality. UHI can be reduced through the use of trees and vegetation, so they provide a lot of shade and cooling effects. And we can also measure and quantify UHI and other info through satellites and remote sensing, as you can see in the photo in the bottom right. So here are some examples of NASA satellites and remote sensing. So the purpose of these satellites are to map the Earth through sensors that capture energy across various wavelengths of the electromagnetic spectrum, and they split them into different bands, such as infrared and visible light, and they calculate metrics that quantify the Earth's surface. For the scope of my project, I focus on Landsat, and the spatial resolution for this is 30 meters, which means that each picture it takes encompasses 30 meters. The spatial resolution is 16 days, which means it takes 16 days to circle back to the same place that it started at. So my research question was, in Orange County suburban environments, how do trees help to benefit the quality of life and the environment? And where should we place these trees to maximize their benefits? To answer that, I asked, how do climate and environmental factors impact tree health and benefits based on tree ring and satellite data? My research goals were to characterize how trees and the urban heat island effect contribute to health and environmental consequences of climate change. To do that, I developed a regression describing the relationship. So why is this research I'm doing important? It's because I live in an area in the Orange County suburbs where there aren't many trees and we have to drive to get anywhere, even to the park. So I believe that investing in trees can make life better by improving health and environmental conditions that I talked about earlier. It creates walkable cities and human-friendly infrastructure. And doing research like this informs policymakers and decision makers, and it can help to improve the world by helping those in charge better understand how to improve the world, which helps me see my personal impact on the world. So the way I want to go about doing this would be splitting this project into two distinct parts. The first part would be analyzing tree rings to find relationships between the climate and the tree growth to know the optimal conditions for the trees. And second, I would use Google Earth Engine to apply this to my area and understand where exactly we should place these trees to maximize their benefits for the people and the environment in mind. So this is for the people who want to see my work more in depth and the extent of what I did. So here's my GitHub and my Google Earth Engine if you'd like to see those links. These are just resources for people who are more interested in that. So this reading spreadsheet is from Isle's dissertation, where each row gives a single year of tree with its standard ring size, the climate conditions such as precipitation, solar radiation, as well as temperature and location. There were hundreds of trees in this dataset, so I had to find a way to group them, and I chose to do that using ecoregions. On the right, you can see a map of all the California ecoregions. So I aggregated data by ecoregion and then made relationships based on the climate factors versus tree growth for each one. So I used Python to match each tree to the respective ecoregion, and then I graphed each one, its climate condition versus the tree growth. So for this particular example in the right, we can see that we have the temperature versus the standard tree growth for the Mojave Basin and range. As we increase the temperature, the tree growth decreases. And to understand the statistics, there is the R and P value at the bottom. So the R value is the correlation coefficient measuring the strength and direction of linear association. A negative R value means negative correlation, and positive R value means positive correlation. When it's closer to 1, that means it is much stronger. A p-value, on the other hand, measures statistical significance. So a p-value of less than 0.05 is considered statistically significant by showing the correlation is unlikely to be caused by random chance. So I gather results for all the ecoregions and climate conditions, and I saved them based on whether they were statistically significant or not. So I got 20 usable figures, and I condensed that into a bar graph that you can see below. So some basic conclusions I made were that precipitation led to more growth in all the ecoregions I analyzed. Solar radiation led to less growth in all the ecoregions analyzed, while temperature, on the other hand, was more inconclusive and environmental based. For desert regions like Mojave Basin, the R values were very high and more sensitive due to having a lack of water in those areas. On the other hand, mountainous regions like the Sierra Nevada were more complacent because they had more water sources nearby them. For the second part of my project, I worked on Google Earth Engine. So this is an aerial satellite view from NASA's Landsat of my area, Orange County. And the code I'm using here has been built up over time from IO and past interns in this internship. So the purpose of this program is to assess the urban landscape and make conclusions. What I did to add onto the code was grab 1,000 sample points and then measure the metrics at each one to make conclusions. For each point, I got 3 metrics: the normalized difference vegetation index, NDVI, normalized difference built-up index, NDBI, and land surface temperature, LST. NDVI is a measure of how much vegetation there is in an area given by that equation. NDBI measures how much urban structure there are in impervious surfaces based on that other equation. And the land surface temperature measures how hot the Earth's surface is at a specific place. So from the results, I found that there's a very strong negative correlation for NDVI minus versus LST and a very positive correlation for NDBI versus LST. In simple words, more vegetation led to less heat, while more impervious surfaces like concrete and asphalt led to more heat. So I propose that urban planners can look at maps at areas with little vegetation and lots of impervious surfaces and prioritize those areas to place more vegetation in order to reduce the urban heat island effect. My next steps are to see how far I could take this program and create an index that could show urban planners where exactly to place these trees. And this program is also applicable all over the world. As you can see, this is the program working in New York where Io lives. I plan to meet with Io monthly, and we want to work on a future project with Jawad, another one of Io students, and Dayton, my brother. We hope to possibly present research at a national conference like the ESA 2027 annual meeting, where Io is a part of the organizing council for public affairs and policy. So this is my works cited. I used Io's dissertation, which included the tree data and the code and a lot of other foundational information. I couldn't have done it without him, and some other scientific journals that I used. And before I end, I'd like to take a moment to thank some people. So I actually met with Io in person in New York, and we ate this restaurant called Leon's. And on the right is the chef, Nick. So most of all, I'd like to thank Io for guiding me all throughout the way in this internship. I'd like to thank Lynn and Ariana for making this a great internship experience, and Jawad for we like to work together on the next project. And last but most importantly, my family for being so loving and supportive all throughout the way, no matter what. Thank you so much for listening.
Thanks, Dawson. I didn't know you got to go to New York and meet in person. That's incredible. Amazing. Does anyone have any questions for Dawson?
So Kevin asked, how did I account for clouds in the imagery? So in the Google Earth Engine code, there's a cloud mask that get rid of the gets rid of the clouds. So if I go here, so this section of the code masks the clouds to count for that and make sure it focuses only on the land. And Kaysen asks why the R values for my graphs weren't close to 1, but rather they're quite small. So for example, here in the Mojave Basin, it's the R value is 0.47. That's because in regions there are many factors that go on besides just the precipitation. So it's impossible to keep track of all of them, and they're all constantly changing. It would be perfectly 1.0 if the only factor changing was the precipitation. Owen asks, why did I choose to aggregate the data based on ecoregion level 3 and how did I do that? So I chose to aggregate based on ecoregion level 3 because level 2 was much too big while level 4 was too specific. So this is a perfect in-between spot to aggregate the regions by density. And I did it by using a spatial join by looking at the shapefile of the EPA and combining it with my code.
Um, Thanks, everyone. You're really demonstrating such a deep understanding of your work, Dawson. This is so great to see. Alrighty.